Greetings. The goal of this presentation is to give an overview of the concepts behind the modules of the FracApp that use surface drilling data to generate geomechanical properties, optimize completions, forecast production and economics. The app has 4 different modules which are integrated in one platform and represents a seamless workflow. The CMSE part of Drill Predictor lets us derive the pore pressure, stresses, and geomechanical properties along the wellbore using commonly available surface drilling data. The completion design module lets us leverage the extracted properties from the drilling data to optimize completions and improve cluster efficiencies. The results of the completion design are then used to estimate the well performance using a trilinear model which is embedded in our prod predictor module. The production forecast is then fed to the EcoN predictor, which is a comprehensive economics analysis tool. So the workflow behind Drill Predictor is based on the concept of MSE, which stands for mechanical specific energy. However, it's corrected for the frictional pressure losses to get accurate estimates at the bid. Surface drilling parameters such as ROP, RPM, torque, weight on bid are used as inputs to the model, along with the wellbore survey, geometry, and the other BHA information. A comprehensive torque and drag model then corrects for the friction losses to estimate the corrected MSE. On the other hand, the confined compressive strength is estimated using various subsurface inputs such as the overburden gradient, mud weight, and the internal friction angle. Now the CCS is basically the energy that is required to break a unit volume of rock, and the CMSE is the energy that is spent to break a unit volume of rock. So the ratio of the two gives us an estimate of the drilling efficiency or the drilling energy. Once we have the drilling efficiency, we then fit a trend line on this dataset, similar to the trend line fitting approach used in the porosity-based pore pressure estimation techniques. This trend line is analogous to the normal compaction trend line, and it lets us capture the pore pressure trends and stress variations along the wellbore. In the next step, the geomechanical properties are calculated based on various lithologic-driven correlations, which we can then use for various applications such as geosteering the well in the most frackable rock, landing and staying in the right zone, as well as optimizing our completions based on one of the reference logs derived using this workflow. So that was the summary of the entire workflow. Now I'll dive into the details of the individual steps. So I mentioned we use drilling parameters such as the weight on bid, torque, ROP, RPM, and in case a motor is used for directionally drilling the well, then we will also need the differential pressure and the flow rates to estimate the corrected MSE. Once we have the corrected MSE, we then use it along with the confined compressive strength to compute the drilling efficiency. And as I explained previously, the plot here shows the fit of the trend line, where the variation of the drilling efficiency data from this trend line or baseline gives us an indication of how the pore pressure is going to vary from the normal hydrostatic pressure. The fit of this trend line can now be refined by calibrating the model with deep-fit interpreted values of pore pressure and closure pressure. Lastly, the computed rock strength, pore pressure, and the stresses are used in combination with correlations based on lithologic variations to estimate the rock mechanical properties such as the Young's modulus, Poisson's ratio, shear modulus, porosity, fracture index, which is basically a normalized fracture density log, as well as stress brittleness, which is an interesting parameter defined here. So instead of a conventional brittleness, we combine that with the differential stress, as we know that high differential stress could become a frac barrier. So we combine the two to optimize completions, for example. In terms of validations, here we are looking at the calculated static Young's modulus and Poisson's ratio using surface drilling parameters by FracGeo, and that were compared with the wireline dynamic Young's modulus and Poisson's ratio in the Woodford formation, and we observed similar trends between the two, capturing the relative variations in the rock properties that could potentially drive the differences necessary to optimize completions, for example. Here in the Workflow dataset, we are looking at the comparison of microseismic response versus the shear modulus, one of the mechanical properties calculated again using the surface drilling parameters, and we see that we are able to capture the rock properties that is driving these differences in microseismic activities, where we have high microseismicity, or we see high shear modulus, and when there's lack of microseismicity, we have low shear modulus. In the same work, we also calculated the fracture index. Basically, the idea is to be able to discriminate which parts of the well are fractured and which are not fractured. And so we can see here our fracture proxy on the left compared with the interpreted FMI on the right, where we have a direct measurement of the conductive fractures. And we see a nice correlation. Where our fracture index is high, we have high fractures, and where low, it's low. So again, it's a powerful tool for understanding the fracture distribution as well. And of course, if you have any seismic data, you can start looking at the faulting and see why we are picking up these faults on the fracture index and validate it just like we did here with the FMI. And in this Wolfcamp example, we show here a comparison of the Young's modulus that was calculated from pre-stack seismic inversion versus the Young's modulus using drill predictor. So we see we have similar trends. Of course, the magnitudes are different in this case because seismic is measuring the dynamic Young's modulus and drill predictor is capturing the static measurement, kind of like what a core would measure. So if you have core data, you can validate against that as well. But again, it's powerful to have both because now we can come up with a function that relates our static properties to our dynamic properties, which means we can convert our 3D seismic related elastic properties to static properties, which is what we need for our engineering workflows. Moving on to the next module of the workflow, which is the completion design. So once we have the geomechanical properties along the wellbore, we then use them as reference logs in the next step to optimize the completion design. So we initially start by designing a geometric design based on the limited entry technique, which results in an initial cluster efficiency of 52% in this case. The table here shows the depths of the clusters, and the color code highlights the differences based on the selected reference log, which is in this case the SH-min. So we notice that there is high SH-min variability in multiple stages that would then cause some of the clusters being overly treated as compared to the ones that are placed in high frac gradient rock. So based on the variability of the SH-min within the stages, we then reposition these clusters in a way that they are placed in rocks with similar frac gradients, so they break at a common treating pressure, and hence we achieve better cluster efficiency. This optimization can be done either manually or using the auto-optimize feature, which detects the inefficient stages, and then based on a user-defined threshold, it repositions the clusters in a way that improves the overall cluster efficiency. In this particular case, we were able to improve the efficiency from 52% to 78% just by placing the clusters in light rock. Moving on to the next step of the workflow, the prod predictor lets us estimate the production forecasts and reserves estimates using a quick and robust analytical solution without a lot of input data and computation time. The unique feature about this module is the implementation of the physics-based analytical trilinear model that bridges the gap between the full numerical reservoir simulation and the simplistic decline curve analysis. The trilinear model considers three different regions, namely the hydraulic fracture region, the inner reservoir which is naturally fractured, and the outer matrix reservoir. Using these flow regimes, the Darcy's flow equations are rewritten by using dimensionless variables. and the coupled equations are solved in the Laplace domain to estimate the results. Moving on to the last module of the workflow, the EcoN predictor helps us distinguish between different completion scenarios by estimating the underlying economics of each simulation design. Some of the highlights of this module is its ability to tie the production forecast estimated by the prod predictor and account for all the cost to handle the challenging business decisions with performing a comprehensive economic analysis. This slide shows the comparison of the results from EcoN predictor and PhD win, and we see that the key economic parameters such as the NPV, ROI, IRR, and the payout match reasonably well. With that, I would like to conclude by re-emphasizing the importance of leveraging surface drilling data to answer the very important issues of frac stage optimization, cluster spacing, landing and staying in zone, using the real-time feedback from the geomechanical properties, pore pressure, and stresses. The workflows and validations included in this presentation have been extensively published with major operators in the Wolfcamp, Eagle Ford, as well as the Vaca Muerta basins, and the user manual of the FracApp contains the links to access these papers. The next series of videos will go through the step-by-step details of running the individual applications as well as some of the techniques to interpret the results. With that, we appreciate you taking the time to learn about our new cloud-based technologies and look forward for your valuable feedback to keep improving our applications. Thank you.